Okay, Bismillah ar-Rahman ar-Rahim, wa salatu wa salam ala ashrafil mursalin, Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Assalamu alaikum, everyone. Today, inshallah, we're going to be doing the real geometric control, okay? And this will be, we're going to be taking SO3 as an example. Hopefully, inshallah, we're going to be finishing this in 2 lectures. So we're going to be first looking at the stabilization control on SO3. Then we're going to be looking at stabilization control on SE3. And I'm still in doubt whether we're going to be doing the tracking version of it or it will be an extension that you can read at home, okay? So let's start with a recap as usual. So we finished Lyapunov's direct method. We said, okay, it's a method where you can analyze the stability of equilibrium points for a given nonlinear system, and it can providing some criteria. You can check whether this equilibrium point is stable, asymptotically stable, or globally asymptotically stable, as we discussed. Then we said that in case we only face negative semi-definiteness of the Lyapunov function's derivative, then we can extend this analysis by what's known as Lassalle's invariance principle that tells you, you know what, instead of, if you can find actually, if you can characterize all of the set of points where V dot is equal to 0, exactly equal to 0, where V dot vanishes, we call this set R, and we find inside of the set R the largest invariant set, which we called M, and if you can check whether this M contains only the equilibrium point that you're interested in, then you have a guarantee that actually this is a locally asymptotically stable equilibrium point. But not only that, Lassalle's invariance principle also gives you an estimation of the domain of attraction. And this domain of attraction is simply the region where V of x is less than L, and this is the region omega, you know, that we started with. Okay. We looked last time at the point mass. The point mass, we looked at the PD controller point mass so that we can, as you know, this was just a refresher for what you should know. Okay, so this is simple, it's a linear system and the controller is linear, but we want to remember how it actually looks like. And then today we'll see how we're going to actually continue with this PD controller, and this will be the path we're going to be taking to SO3. And I'll show you in a bit how. So the point mass dynamics are simply the Newton's law, and kinematic equation. So rate of change of position is equal to velocity, rate of change of momentum is equal to applied forces. And we wrote this in terms of the psi and the p and the v in this way. So we wrote it in terms of that the state was the position and the momentum, and we left here explicitly the velocity, which is p over m. We can simply substitute, you know, v with p over m, and this will be a differential equation in terms of psi and p only. Okay? But we leave it like this, okay, because that will make the analysis easy, as we're going to be seeing today. The control objective was simply to stabilize the point mass at some desired position with some zero velocity. So the point mass is here actual. This is the actual position of the point mass. I want it to come here. And then I change it. I want it to come here, and so on and so forth. What is the controller that can make me do that? Simply, it's a PD control law that you take the error in the position and you also take the error in the velocity, but we said that psi d is just a constant. Okay? It does not change with time, and thus its derivative is also 0. So you see we have here something like a derivative in the, so we have a gain multiplied by the error position and a gain multiplied by the error in velocity. And if we take this control, sorry?
We assume that V is fixed?
You mean the V psi dot, you mean? The desired point where we want to go to, it's not changing. And this scenario I just mentioned where I want it to be here, this is the point mass and I want it to go there, you change it in what's known as a piecewise continuous manner, which means that at one instant it's here, and then it disappears and it goes there. Okay, so every interval you consider it to be psi d is constant in that interval, even though it's changing, but it's not like you want actually to track a trajectory. That's the tracking problem, where you say, okay, I want it to follow, for example, a circle, and it follows that circle exactly. So that's a tracking problem, not a stabilization problem. Okay, and then when you plug in the control law U that we just devised here, and we put it inside of the dynamics, this would be the closed loop dynamic system. And actually, it's written like this. It's simply just an x dot equal to some function of x. But actually, you can rewrite it as a linear system. In the end, it's just linear matrices inside of, so there are linear operations there, matrix multiplication and addition and subtraction. So everything is just linear. And you can, you can test the stability of it using, linear analysis. So this is actually A minus BK matrix, in a linear state space form. We're going to be doing today with the Lyapunov method, but the goal is not actually the PD controller. So the whole idea of the point mass is simply just a toy problem. We want to take these ideas and go to SO3. And you remember what we said last time is that this idea of taking the error on a manifold is not possible. So taking an error on the manifold simply as the difference between 2 points, the desired and the actual point on the actual configuration is not possible because of we don't have a vector space structure. And this idea of how the velocity actually is related to the position, simply that rate of change of position is equal to velocity, that's only in R3. Okay, it's not in general applicable. Yes, now.
This is a little side question, but why did we start from PD, not PID, or not PI, or not PID? And another thing,
Yeah.
this might have some relevance. I have worked on quantum circuit drone.
Okay.
And their MATLAB whole design system of controlling the drone was also PD.
Yes, right.
So is there anything that, like for quad rotors, or that we essentially go towards PD by twice?
That's a very good question. So I'll rephrase the question. Why PD? What was so special about the PD? Hopefully, when we generalize this, you'll actually see why. Actually, the answer to your question is in this part. Actually, we're going to reformulate the simple PD controller. It looks very innocent. Any bachelor student, should know this PD controller. And there are, of course, more complicated versions of it. But here, you see, we're going to be reformulating in a way that will enable us to generalize it to SO3 and SA3 and in general. And it will partially answer this question. For mechanical systems, why is the PD, very special? Okay. So this is the way we're going to be reformulating it. So a PD controller is simply a proportional term and a derivative term. Makes sense, right? And the proportional term is the sum gain multiplied by the error in position, and the derivative term is sum gain multiplied by the derivative of that error. We can also think about this term here, minus Kp multiplied by the error. You can think of it actually as the minus of some, so the UP, so this proportional term, you can think of it as the gradient of some potential function psi, potential function capital psi, that's a function of this psi variable, psi. Okay, so psi and psi. You have to be careful with the symbols here. So this is capital psi, psi, and this is capital, and this is small psi, xi or xi. Okay, so that's a position exactly. Yeah. So a potential function as in terms of the position. And this potential function is simply half psi minus psi desired. Remember, psi was actually an R3 vector. So R, psi minus R psi desired, this is R3 vector, transpose multiplied by Kp, multiplied by psi minus psi desired. So this form, okay, is simply, okay, if you take the gradient of it, okay, you can just eyeball it. The gradient of this function is Kp multiplied by psi minus psi desired, right? This is very similar to half mv squared. If you take the gradient of half mv squared with respect to v, what do you get? mv. Okay, so m multiplied by the v, something like this. Okay. If you look at the properties of this function, what does it remind you of? It's exactly positive definite, but not only that, it's also radially unbounded. What's actually this function? How does it look like? It's a quadratic. It's a bowel. It's a parabola. In general, right? In all directions. Even if I have in ND, it's still it's a parabolic function in ND. And the gradient here is simply I take this function and I similarly as we discussed earlier, you know how the gradient works in Rn. So this is trivial for you. Make sense? Everyone agrees? Clear? It's an easy fix, right? And now let's do Lyapunov analysis with the closed loop system. So the closed loop system which is this one, now the controller comes from, I reinterpreted this Kp multiplied by psi minus psi desired as some gradient of a potential function. The Lyapunov function I'm going to be using here is actually the original Lyapunov function the system had, which is in this case for this problem is half 1 over 2m p transpose p. Does anyone remember what was this?
Momentum.
And what is this term? P is momentum, and what is this term? Energy, kinetic energy, exactly. This is equivalent, I showed you last time, this is equivalent to half mv transpose v, right? So this is half mv squared, but written in terms of the momentum, not in terms of the velocity. So this is this term, and this term is simply the potential function we derive the controller from. Make sense? okay? And now this is the v, and this is a quadratic function in terms of the p, and this is another quadratic function in terms of the psi. So the combination of both is another quadratic function. Make sense? To check whether this is positive definite, okay, simply do the, remember the analysis we looked at before. Let's look at the Hessian of this function, and you can simply see that it's actually kp and zeros and 1 over m multiplied by the identity. So here I have psi d is a constant. It's just some number. So when I differentiate twice, it will just disappear from the equation. Okay, and then I have the psi, and you see I have half kp and psi, something like psi squared. So this is why the kp appears here alone. So this is very similar to what we did earlier. We know with the quadratic Lyapunov function, and this is the kinetic energy I get here, 1 over m multiplied by the identity. And of course, 1 over m multiplied by identity is, is positive definite by nature. It's a positive definite matrix, it's just the identity. And the kp, you design it. Remember what we said about, actually we choose the kp to be just positive. Usually, by the way, this is actually a little bit of a generalization, because the way you're used to PD control is that, not that. That actually, the kp, you think of it as just one number, or a diagonal matrix, right? I have psi, for example, psi minus psi desired is x minus x desired, y minus y desired, and z minus z desired. So you always think of kp as k1 and k2 and k3, like k1 multiplied by x, or kx multiplied by x minus x desired, ky multiplied by y minus y desired, and kz multiplied by z minus z desired. But this is actually a generalization. So this is just a diagonal matrix key. But I can also choose some coupling. I can couple the x and the y and z if you want. If your application needs it, you can couple the x and the y and the z, and the kp can be fully symmetric. Okay. So here we actually require kp to be positive definite, which means it should be symmetric, and it means that in general I can have off-diagonal terms, but the kp completely just needs to have its eigenvalues greater than 0. Okay, so that's the generalization of the v. So now we have that the v is positive definite. So this is the Lyapunov function. Let's calculate the v dot along the trajectories. So v dot in general is equal to, so this was the expression, it should make sense to you. Okay, we compute the differential of v with respect to x, and we pair it with x dot. And you remember that the x here, so the x we're talking about here is psi and p. So I have psi alone and p alone. And the v, which is a function of x, I can separate it, in this case, it's naturally separated into one function on psi and one function on p, right? Yeah. Which means that I can rewrite this expression, which is I'm taking x dot living in R6. I can think of it as two parts. One which is psi dot, one which is p dot. Make sense? Yes. And then I have the differential of this function with respect to psi, and differential of this function with respect to p. And we said that the differential of this function, so you remember we mentioned something before, that there is a relation between the differential of a function and the gradient of it, which is the transpose of it, remember? So we said that this actually expression, I can write it as this multiplied by that, so this transpose multiplied by that, and this is a scalar, but I can write it as x transpose y or y transpose x. So this is the other way around. And this expression here is simply also the gradient of this transpose multiplied by p dot. Make sense? So is this clear how to go from here to here? After that, you can replace the psi dot and the p dot with what? How do you continue calculating the v dot?
Yeah, the psi dot is equal to the p.
You have to use what? The dynamics. So you see we have the closed loop dynamics there. We know that psi dot is equal to velocity, and we know that p dot is equal to this expression. Where did this expression come from? It is the closed loop dynamic, but what is p dot equal here to? The controller, right? So the first term is the proportional term, and the second one is the derivative term. Okay. So now if I plug in here p dot with this expression and psi dot with that expression, what happens? What do you see goes? This term cancels with that term. And then I'm only left with something that looks like this. V transpose multiplied by UD. So you see what we did here? We said that our proportional controller is the gradient of some potential function. And that same potential function, I can actually plug it in. I can do with it the Lyapunov analysis. And we did not say how the UD should be. We did not say what the derivative term should be. But from this expression here, when you're doing Lyapunov analysis, what do you want the V dot to be?
This is greater
Greater than V dot? Less than. We want it to be negative semi-definite, at least or better, negative definite, okay? Here, the natural choice of the UD is simply to choose it to be minus KD multiplied by the V. If you plug in this choice in here, what do you get? You get something that looks like this.
Will always be negative or
It is always, this is a term, this is negative semi-definite or negative definite, V dot. Why semi-definite?
Because we don't have the psi.
We have only a function of V, not psi. Remember, the V was actually just P over M. Okay, so this is still in a function of P. So we're left here with a function only of V, or in equivalently P, and I don't have psi, which means, as we saw earlier, this is only negative semi-definite. So what do we conclude from here?
local asymptotic stable.
No,
Stable.
only stable,
No, but it's less than or equal 0
which means.
locally. Yes.
So what is the theorem you're going to be using to continue? So how do you prove? How do you continue? You say no. But if I stop here, what should I conclude? Using Lyapunov's direct method, we have a proof that the equilibrium point, which is here in this case, was psi desired and 0. Did we check that psi desired and 0 is actually an equilibrium point of the system? We did not check that, right? What we should do is that we should plug in here the V. Let's go back to the V. One of the things to actually check for that, we must plug in here the equilibrium point we want. So we must plug in here psi desired and V equal to 0. Let's start with the V equal to 0. What happens to the P? It becomes 0, so this drops out. And if I put here psi equals psi desired, this also becomes 0. So we have a proof that V of 0 is 0. V at the equilibrium point is 0. And the equilibrium point here is not 0, by the way. The equilibrium point is psi desired and V, and 0, sorry, and V equal to 0. So psi is equal to psi desired, and V is equal to 0. That's the equilibrium point. So now we had that V is equal to 0. And now, up until this point, we find that we have only stability. How to continue? Lassalle's invariance principle. I'll say it very quickly because it's exactly what we did earlier. Remember, I told you, Lassalle's invariance principle is just you can always eyeball it. V dot is equal to 0 when? When V is equal to 0. If V is equal to 0, what does that mean here? The first term is 0, so psi dot is equal to 0. And the UD, you remember what was the UD? UD was equal to KD multiplied by V. So also UD is 0. So this is 0 and this is 0. I'm left with this term. Okay, so the gradient of that. The gradient of that term, when is it equal to 0?
At the equilibrium position.
Exactly. So this gradient term, where was it? So this gradient term, when is the gradient term equal to 0? When the error is equal to 0. So in the end, the largest invariant set has only one point when the error is equal to 0, or alternatively when psi is equal to psi desired, and the velocity is equal to 0. So all of these conditions, just write them one after the other. Now you have the omega, you have the r, and you have the m, and thus using Lassalle's invariance principle, you actually have that the equilibrium point is locally asymptotically stable. Why do we say here that it's also globally? First of all, there is only one equilibrium point. What else?
Radial unbounded.
This Lyapunov function is radially unbounded, and thus I have only one equilibrium point, and it's asymptotically stable, which means that it is also globally asymptotically stable. Okay, so you see how we use the mix of Lyapunov, Lassalle, and Lyapunov again to actually show that this is stable. And by the way, this is actually a linear system. Remember what we said? This actually was a linear system that we derived here. So if we go back to this system, this is linear. And actually, the equilibrium point it has here is simply psi equal to psi desired and V equal to 0. And you can just check simply here by, A minus BK, it has eigenvalues, blah, blah, blah. greater than 0, and you can always check that this is actually the case. The bottom line, we did not need to do Lyapunov analysis, but the whole idea is that you see for this, in this way of reinterpreting PD control, we can actually generalize it. So in general, when we say PD control for a general mechanical system, you can always reinterpret the potential term as something that shapes the energy of the system or changes the Lyapunov function that you have. You see, this was the original Lyapunov function, which was kinetic energy. And this term, what does this term actually remind you of? So what does this remind you of?
Controller input.
No, in terms of energy.
This is also similar to
Similar to what?
The potential.
Potential energy of what? Half delta x transpose k delta x. What does this remind you of? A spring. The potential energy of a spring, exactly. So you see here, what is the proportional term doing? It's like I added a virtual spring to the system. And what is the damper doing? Sorry, and what is the derivative term here doing? It's like I have a damper here. So I started with a point mass, and the PD controller is simply I added what? I added a spring and a damper to the system. So in the end, the closed loop system, actually go back here, that's a check for you at home. Take this system, forget about it, and take just a mass spring damper and model it. And see actually how it looks like. It will be exactly like this. The mass and the spring and the damper.
Kp actually serves as a B from the mass.
Kd is the B, is the friction coefficient,
Yeah, B.
and Kp is the stiffness of the spring. Okay? In general, you can generalize this idea of that a PD controller is simply just a mass, a spring and a damper to actually general nonlinear systems. Okay? And now if you think of any other system, and it's just some inertia like the quadrotor. The quadrotor is just some inertia. Okay? How to stabilize it? PD controller, because the spring will make me go to where I want to, and the damper will damp the motion. So I have this idea of asymptotic stability.
And how does if I term was injected, how does that?
I is simply, the I term in the PID is simply eliminates the steady state error. It's a way to say that actually, if my dynamics is not this exactly, but I have some errors here, I want to eliminate it.
Then why do we intentionally skip item over here? Because there would be certain errors.
That's an excellent question. So why would we not look at the I term? Let's keep that till lecture. I have to mention it later on, but not now. For now, this is just a theoretical system. So this is just a toy problem, theoretical on paper.
This only works when we have the 100% correct dynamic knowledge.
Absolutely, yes. And no disturbances here. We don't have any disturbances. If you had disturbances, the I term is just for the disturbances, not to stabilize the system. Think of it this way. Yes, Ammar.
For the, what is it called? Can you go? Yes.
Here?
Yeah, for the V.
For the proportional term, yes. For the derivative term.
Next slide.
Next slide.
For the V, can we always choose these functions as the ones that for the controller on the manifold?
On the manifold, that's another story. This is still in Rm. This is still in Rn, right? So this is the kinetic energy that we already had.
Okay.
And this is the potential energy that we added from the controller. On the manifold, we'll try to do something similar. That's exactly where we're going, yes. Okay, but it will not be as nice as this. Can anyone say it will not be, why it won't be as nice as this on a general manifold?
because we cannot have simple addition and subtraction.
Exactly. We don't, because we don't have addition and subtraction on a general manifold. It does not. This requires what? What kind of structure this requires? A vector space structure, right? If psi and psi desired, I can take 2 points in Rn and I can subtract them and from each other. This is a way to define an error, right? And this is actually, if you think about it, it's just a vector, that goes from psi to psi desired in Rn. If you think about it as 2 points. So now this is the conclusion that the PD controller that we just looked at, I can reinterpret it as a sum of an energy shaping term UP and a damping injection term UD. If I choose here a locally positive definite function psi of the position, and I design it such that psi desired is a minimum of that function, then I can always choose the proportional term to be like this. And if I just plug in the V dot, I will always get this term here by construction. Okay? No matter what I do, I will always get this term there. And thus it's natural how to continue. I just choose the UD to be some function of the V. So I can choose the UD to be some function. It can be in general, by the way. I can actually have a nonlinear function here of the V. And here even the psi, I can have it to be, can have a nonlinear function of the psi itself, of the position. And I design it such that V dot is less than or equal to 0. And then using Lassalle's invariance principle, I can show that this is locally asymptotically stable. How can I show that this is actually globally asymptotically stable? I can also make sure that this is not just locally some positive definite function. I can choose a globally positive definite function. Of course, provided that the psi itself allows you to do that. Remember when we had the pendulum, by construction, the pendulum did not allow us to have, a globally asymptotically stable point because we had more equilibrium points. Okay. Make sense?
Yeah.
So this is how, from now on, we need to think about PD. Take this idea, okay, and now let's generalize it to SO3. Okay. We're going to have our PD example that corresponds to SO3, and this is an example of a rotating rigid body. The equation of motion that psi dot is equal to velocity, so rate of change of position is equal to velocity, on rotations looks like this. Make sense?
Yeah.
And the equation that says rate of change of momentum is equal to applied forces on SO3 looks like that. Rate of change of angular momentum. J here is a constant. It's the moment of inertia of this rotating body. This body is not moving. Okay, it's only rotating in its place. Okay, you can think of this actually as just if you want to visualize something. This is actually either a satellite, in orbit, or this is the attitude controller of a quadrotor. It's fixed in place, and you're trying to only stabilize its orientation. It's not moving and translating at all. So in that case, J omega dot, which is the rate of change of angular momentum, is equal to what is this term? Does anyone remember? Coriolis it was in the translation. In the rotation part, it was called gyroscopic torques. So these were the gyroscopic torques, and I have here the tau. Tau is the control input I apply. Okay. Instead of writing it like this, I can write it like this, right? So the wedge here is the cross product. So the cross product of x and y is the minus the y and x. We can reformulate this equation in terms of the angular momentum like this. Does it make sense for everyone? Okay. So I introduced a variable here called p. Just like what we did earlier, we introduced a variable called p, which is mv. I introduced a variable here, which is j omega, and I read the equation in terms of this variable. So now the states are r and p. So position and momentum, angular momentum. So angular position, something like, it's a position-like variable, but of course here it's a matrix, which is the rotation matrix. And the momentum-like variable is this p. I can put it in state space form like that. Remember we discussed something before that r dot is equal to r multiplied by omega tilde. I can think of it as a map that eats the omega and gives me back the r dot, right? It's something like this. So this beta here is simply, if you give me the omega, I will give you r dot. Okay? That's what we call beta. Okay? And the second term here is a cross product of p and omega, which I can write as p tilde form multiplied by omega. Make sense? This is the point if you want to stop me, because we're going to continue on the same point. If there's nothing clear, let me know. Last chance. Everything's clear? Okay. What is a geometric PD controller on SO3? What we want to do is have a proportional torque and a derivative torque. And our equilibrium point is R desired. Okay? I want the quadrotor or the satellite to have some desired orientation like this or like that or like this. And how do you represent this? Euler angles? No, with an R matrix. So this is the current R, this is the actual R. So current R and desired R. So this is the R that I have, and this is the desired R I want to go to. Okay, so I just changed the R. So this is the R desired, and we're doing a stabilization problem. I don't want to have any angular velocity. Tracking would have an angular or desired angular velocity, but just stabilization, I don't have any desired angular velocity. And I plug in this term into the closed loop. This is the closed loop system. Make sense? How do we proceed? The hashing of this, no, we're still not yet.
We can reformulate it in terms for V or the Laplace function.
Exactly. So now we can think of the proportional term that comes from the gradient of some potential function psi of r. Okay. And it must, we will design it such that it has a minimum at r equal r desired. So that's something you can design. And afterwards, we're going to be choosing tau desired such that we inject damping. Exactly the same as what we did for the R3 example. Make sense? Now, easier said than done, of course. This part, just, this simple controller will take us, at least 2 hours, okay, just to put it on the board. First question is, how do we design an error between R and R desired? If I tell you this is where the satellite is, and I want it to go to that orientation, how do you characterize the error between them? That's the first question. The second question is, how do we design this potential function such that it is positive definite? This is one of the requirements. It has to be positive definite. And it needs to have a minimum at R equal R desired. Okay. Afterwards, we need to compute the gradient. And of course, you remember what was the gradient? So it was this number, partial derivative, exactly, of the function with respect to the components of the vector. So partial f by partial x1, partial f by partial x2. Yes, no.
This is still rotation, no translation.
This is only rotation, yes. Only rotation.
The manifold you have drawn,
What?
that covers translation as well, no?
Where?
This
This is SO3. A point here is a rotation. Right? This curve is that the R is changing. You see, it's changing with time. Okay? So there is no such thing as a gradient on SO3. So that's the bummer. Okay? There is something called the differential. The differential is general. It lives in the tangent, the cotangent space. But something that's just partial f by partial, partial by f by partial doesn't exist here. So we need to work with the geometric object. Okay? And afterwards, we don't have a controller which is in a cotangent space. We have a controller that's given actually by the torques. So how do we take this cotangent vector, okay, covector, so how do we take this covector, which we calculated here, and we transform it into a torque? And now you have a torque that you can apply to the system. So there are 3 numbers. Okay? So you see how we're going to go. This will be the error, and after the 4th step, we're going to have something like torque that's a function of that error. Okay? Don't expect it to be minus kp multiplied by that error at all. Okay? And afterwards, the derivative control. The derivative control will be a piece of cake. Okay? In the end. Okay? So if we're lucky, we're going to finish the first 3 today. Okay? First thing, the error between R and R desired. So all of these are the 3 frames we're talking about. We have some inertial frame, some fixed frame, S, and we have the body fixed frame, B, and we have the desired frame, D. Okay, so orange, okay, black, and blue. So when we say R, what we're actually meaning is R of B with respect to S. Okay? And when we're saying R desired, what do we mean? RD with respect to S. Okay? What is the error we're looking for? B with respect to D or D with respect to B, it doesn't matter. Okay? They're both the same thing. Okay? So what we're going to be calling here the RE, by the way, this is just, this definition, instead of writing B with respect to S and D with respect to S and so on, we're just going to say R and RD and RE. So R is simply B with respect to S. And there's another point here, before I forget. All of these axes are on the same point. Yeah. I just draw them like this so that you can visualize them, but they're all at the same point. So B and S and D, they are in the same place. The error in rotation is simply R D transpose multiplied by R. Okay? And if you just follow the notation, you remember if this R is B with respect to S, and I transpose this, what does it become to? It becomes S with respect to D. So I have B with respect to S, S with respect to D. What do I get? B with respect to D. So this is the RE here. So RE describes the relative orientation of the B frame expressed in the D frame between B and D. So B as seen from D. Okay? That's the generalization of psi minus psi desired, right? We don't have a minus sign here. We just have a group operation. So we multiply the two together in this way. Make sense? So if I want R to go to R desired, what should RE go to?
Identity.
Identity, not 0. So when I have a vector space, and the 2 points, the 2 vectors are the same, I get 0. So psi minus psi desired, I get 0. But here, if the R and R desired are the same, I get identity matrix, right? Make sense? So that's part 1. We're done. So now we have an error variable. Okay? R desired transpose multiplied by R. Second part, positive definite function on R. This we have to cook up. We have to design. It's part of our controller design. You'll find different stuff in the literature. This is the easiest one to start with. Okay? And we've seen it before, remember? We've seen this function before. We had it as an example. It was one of the functions on R, and we showed actually it was positive definite. How did we do that? Does anyone remember? When we talked about it, it was something like this. It was half transpose of I minus R. We did not write it RD transpose R. We just wrote here R. And the RD is just a constant, remember? It's just a constant matrix. So it's just, I'm just multiplying this by a constant. Exactly the same as what we had in the potential function of a spring. It's psi minus psi desired. The psi desired is a constant. It just does not change. So this is the function here that we're going to be using. I multiply R desired transpose with R. So I calculate this error. And I subtract identity. And I take the trace. What do I get afterwards? I get a real number. So this is the psi of R. Something that eats a rotation matrix and spits out a real number. So it's a function. Is it positive definite? First of all, let's check the positive definiteness of it. Is it a valid potential function that I can use for control? It must be positive definite, and it must have a minimum at the point we're talking about, the R desired. So R desired, if I plug in R equal to R desired, what do I get? Identity minus identity, which is 0 matrix, and the trace of the 0 matrix is the 0 number, right? The 0 and R. So I get here psi of R desired is equal to 0. So that's good. That's the first thing. Is it positive definite? Is it always positive?
Yes.
What is the proof?
If you look at the elements of R, they're always less than 1. So if you take the trace, it's always coming out positive.
If you want, you can do it in components like this. This would do it. We showed in the in the previous lecture when we talked about this, we showed a very fancy way of doing it. We used the Rodriguez formula, if you remember. We showed that this function, you have to go back a little bit to the last lecture, not last one, I mean the one where we discussed this. We showed that this function can be written as 1 minus cosine for some angle theta. Okay? We use the Rodriguez formula in that. And the theta here can be something from minus pi to pi, with pi included. And we've also shown that the psi is equal to 0, that's exactly what we showed here, when we have R desired, R is equal to identity. And this identity is actually equal to cosine theta, so that the theta is equal to 0. So I have 1 minus 1 is equal to 0. So that's the minimum. And when theta, what is the maximum value of theta that it can take? It can take pi. So if it takes pi, what do I get? I get minus 1. So 1 minus 1, 1 minus minus 1 is 2. So that's the maximum of it. So the function we're talking about is 0 at the R equal R desired. And as we move away from that point, we get something that's greater than 0. So it has a bowel shape, locally, of course. So it's a positive definite function. Make sense? Yes, no.
How is that a bowl if negative 2.
Are you sure? No, I should move in positive x and negative x, and I get always 2. You're talking about the function always has positive, it's always up,
The output, okay.
right?
Psi is the output, right?
Yeah. And now what you're talking about is that I move positive theta and negative theta, and I get 2 in the end. And check that for yourself. Theta, if it goes from 0 to pi, this goes towards the 2. If it goes from 0 to minus pi, what happens here?
Minus pi is also minus 1.
Cosine of minus an angle is always
Positive.
cosine of the same angle. So you get the same number here. So you see I'm getting the same number whether I move. So it's actually exactly the same as a bowel shape. Okay? Of course it does not go to infinity. Okay? But it's just locally asymptotically
It
stable.
goes to 2 only.
It goes maximum to 2, from 0 to 2. So it's a function that if you plot it on all of R, of course, we're talking about something you cannot visualize, right? Because in order to plot it, you have to plot it on the manifold R, which is, the manifold R itself is not visualizable. It's a 3-dimensional manifold. And we're already 3-dimensional beings, so we cannot visualize it. We can only visualize 2-dimensional manifolds or 1-dimensional manifolds. For example, the torus, the sphere, you can visualize them. The circle, anything fancy, you can visualize it, but not this one. Questions? Okay. So now we have our positive definite function, and it's a function of the error, okay? Similar to the potential function that we had in R3. Now let's calculate the gradient, the differential of that function. Okay. So now let's go to the board. Board. Not good. In order to understand what is the meaning of the differential function in general, let's go back to differential function on a vector space. And Rn would be a typical example. Okay. How do we actually calculate the gradient? The gradient, which is the partial f by partial, x and all of that stuff. You always eyeball it, but you forgot the first time you were introduced to it. You were actually given something that looks like this. You were told you were given it for the first time. It was very abstract. At that time, you were very young. You don't even remember it. It's just like remember the first time you walked as a kid. Okay, so you'll definitely not remember it. Okay, but this is the generalization of this is the formal definition of what is the gradient. Okay, and the differential of a function. So let's look at so this is part 3 when we're looking at we want to compute the d of psi as a function of R, which we said it will be a co-vector in this space. And to do that, we're going to first introduce the differential of a function psi on a vector space W. So definition. Let psi be some function that eats a point in a vector space and gives you a real number. Okay? So it will eat an x and will give you a psi of x. Okay. The differential of psi is the unique covector denoted by d psi of x, and it lives in this space, in W star, that satisfies the following expression. When I take this covector, if I have a covector, what can I do with it?
Times the vector.
This times what is generalized to?
The product.
The dot product is only an Rn. What is the generalization of it?
Convolution.
We called it the duality product. It was this expression. Okay. Remember? So when I pair it,
Doctor, is it duality product or expectation value?
expectation, what is the expectation?
Expectation value that we do for probability.
No probability here. No, that's something, no. It's not, this is just the duality product. Okay? So this is a covector, and a covector, it can eat a vector and give you a real number. That's how we write it like this. Okay? And this delta x is simply any arbitrary vector in the vector space. So delta x is the name of the vector. Okay? So delta x is the name of the vector. Just, I could have called it y or, or z or anything else, but we just call it delta x. And it's equal to, so this expression should be equal to d by d epsilon. You differentiate with respect to epsilon and you let epsilon equal to 0, of which expression? Of that expression. Of psi x plus epsilon multiplied by delta x. And this is, you do this for all delta x in W. Yes?
What is epsilon?
Epsilon here is just some number. It's a dummy variable. You take, so how you read this is the following way.
Shouldn't epsilon be, sigma be parameterized?
Psi?
Psi be parameterized by epsilon for the differential to be to exist.
That's exactly what you have here. So I have x, it's a function of x. I plug in x plus epsilon, and I add this arbitrary vector. And then after I add this, I differentiate with respect to epsilon, and I set epsilon equal to 0. After I differentiate with respect to epsilon, and I get epsilon equal to 0, the epsilon will disappear. And I'm going to be left only with something that's in terms of the delta x, and will in terms of this covector. Whatever is remaining here is the definition of the covector. Let's take an example. Let's take an example which is Rn. So, example Rn. So let x belong to Rn, and consider the function psi of x equal to half x transpose kx. Have you seen something like this before? That's exactly the potential function we're working with in the mass example, right? It was the error function, right? There I had psi minus psi desired. Psi desired is just a constant. I'm going to, let's put it to 0 to simplify. And the x here is psi minus psi desired. Okay? So this is a function of psi minus psi desired, just to generalize. But just a function of x, I have something like this. If I tell you what is the gradient of psi as a function of x, what do you say? K multiplied by x. You all agree, right? Unanimously. Right? How do you get this? You just know it, right? You just feel it, That's exactly, the first time you walked, you now you know how to walk. How did you do it the first time, you don't know. That's exactly the same. How did you get this the first time, you just don't remember? Differentiate? Okay.
I think we call it in simple calculus ab initio principle, or the first principle to find the derivative of function.
Okay. So you just, you take partial, but you put differentiate with respect to, individual components, right? But where did it come from? Why is this, the general case? And this was the vector version of it. The co-vector version of it, if you remember, we said it will be the transpose of that, which is, it will be kx but transpose. So we know that, okay? How can we derive it from this expression? How can you just blindly give it to the computer, let it derive it for you? Not by memorizing, that this is actually differentiation and so on. Just let it, follow a natural way, okay? A very systematic way. So what we're going to be computing, so if we go back here, you see what we want to do now? In order to get this differential, let's calculate this term, which is psi of x plus epsilon multiplied by some delta x. Delta x is random, not random, I mean it's arbitrary, and epsilon is some constant that we add. Okay, so it's some variable that we're gonna be eliminating in a second. So psi of x plus epsilon multiplied by that term, what is it equal to? Half transpose k. Everyone agrees? And you can expand this expression, right? I have a plus b transpose multiplied by k, a plus b. What does it look like? You have the first term, if you had a plus b multiplied by a plus b, what does it look like? A squared, this multiplied by that, plus 2ab plus b squared, right? Have something similar here. So we have half x transpose kx. So this term and that term multiplied, I get this term. Just similar to the a squared there, but with the k inside. And I have 2, but there's a half here, so that it will disappear. So I get only an epsilon multiplied by delta x transpose kx. And let's remove this part. So you remember this part, okay? So let me just put it very small. Okay. Epsilon is a number. That's actually a very good point. So epsilon, I forgot to mention here that epsilon is simply just a number, a real number. So it's a scalar, yeah. It's not a constant. It's a variable. It's a dummy variable. We put it, and then we're going to be differentiated, and it will disappear. Okay.
It should be k multiplied by. We're taking the term that is.
So let me do it slowly. Let's do it step by step. Okay. So this term will be half epsilon transpose multiplied by kx. And then I have half epsilon multiplied by x transpose delta x. K delta x.
Why there is an epsilon? Oh, okay.
Okay. Make sense? So I just a multiplied by b plus b multiplied by a.
And then the last term?
And this term, you see this whole term is actually just a scalar, right? It's like y transpose kx. So I can transpose the whole thing, and what do I get? If you have a real number and you transpose it, what do you get? The same real number. So I can always retranspose this. So I can rewrite this as half. I get the same term. And then I have half. Epsilon is common.
Did we put the b squared term?
Sorry?
The last term is still.
The last term is missing. Fourth term.
I do not add it yet. Yeah, I'm just taking these two terms separately. I'm only focusing on these two now. Okay. And we have here plus stuff, okay? So let's only take these two, okay? Let's see how they look like. And then I have here this guy, kx, plus that guy, which is x transpose k multiplied by delta x. I can transpose it, and it will become psi. It will become delta x transpose multiplied by k transpose multiplied by x. K is, so the assumption we're going to be making here, for this to be positive definite, k has to be symmetric. You remember when the first time we mentioned the whole, there was a slides where we had positive definite matrices. We said we can talk about positive definite matrices that make up positive definite functions only if they are symmetric. Remember that term? And we said if it was skew symmetric, it would actually disappear. So actually here, k has to be symmetric. It has to be positive definite, which implies actually, so this already implies that K equal to K transpose. And thus all of this term is actually 2 over 2 epsilon multiplied by this term. Of course. Make sense? Okay. Let's see. We need to remove all of that part. So I'll have to rewrite it again.
Maybe you can take another, make it smaller.
Smaller.
Yeah, like
I'll try to, let's see how much time to experiment. Okay, we have 5 minutes to experiment. Let's see. I would like to duplicate this. Let's see. I don't want to delete it. I think, nope. Okay, let's try to copy it. We only need this part. Let's hope it's copy the report. Okay. Ta-da. Okay, nice. Okay. So now this expression, so we see, okay, it's half x transpose kx plus epsilon kx plus, we have something in terms of epsilon squared. I have epsilon squared multiplied by delta x and k delta x. Everyone agrees?
Yes.
Okay. So that was this term. What should I do next?
We will take the limit that
Differentiate with respect to epsilon and set the epsilon equal to 0. What do we get of that term? Okay. What do we get? The first term, is it a function of epsilon? 0. Okay. So all of this term becomes 0 when I differentiate with respect to epsilon. And this term, when I differentiate with respect to epsilon, what do I get? This is just a whole constant multiplied by epsilon. So it's like you have ax, and you differentiate with respect to x. What do you get? A. That's the A. So this is this term. And the last term, when I differentiate with respect to epsilon, what do I get? Something multiplied by epsilon. And when I plug in the epsilon equal to 0, the whole term vanishes. So this whole term is 0. So half epsilon squared multiplied by A. Differentiate with respect to the epsilon, what do you get? 2 multiplied by half multiplied by epsilon multiplied by A. And then forget about what the A is. It could be anything. And I plug in epsilon equal to 0. This whole term disappears. Okay. What are you left with? This is this term multiplied by kx, which I can rewrite as kx transpose multiplied by this term. Make sense? Okay. What is the covector? What is actually the covector that we're looking for? What is this differential function? So you see, the differential of the function is the unique covector that if you give it this arbitrary vector, delta x, we do not specify what delta x is, it could be anything, and I pair it with this, I get actually, this right-hand side. This term, so we calculated the right-hand side now, and this term on R, and how does it look like? So if I ask you, let y be some in this vector space, in the dual vector space, and x be in this vector space, and I tell you, how does this look like? What do you say? In Rn. This is, of course, Rn, and this is Rn star. How does this look like? How do you compute it? If y is a covector, this is equal to y x. There's no dot. There's no dot. This expression, we've seen it before, right? Y, if y is an Rn star, that means I can write it as like a row vector, and I have y1, up to yn. And then the x, so this is the y. And the x, I can think about it as x1 up to xn. And then when I multiply the y by the x, what do I get? A scalar number. That's exactly the scalar number. Okay. If you were thinking about the transpose, then you also represent the y as a column vector. Okay. But naturally, if it appears here, it means it's a covector. Okay. Similar to exactly what we did earlier, with the wrenches and so on and so forth. Yes.
When you actually do it for any system, do you see what's dx, what's the form of dx, and take whatever's left as the y?
Yes.
Is it this way?
That's exactly how it is. So if you go back here, you see on the vector space Rn, so on Rn, the term d x delta x is nothing else than something multiplied by delta x. And this something is what we call the differential of that function. Okay. So now let's go back to what we calculated. So what is the differential of the function psi? So you can conclude from here that the differential of the function psi as a function of x is simply kx transpose. Okay. Of course, I wrote this. This is not correct. Actually, I mean here the d, not the delta. Okay. Okay. Let's see how we wrote it there. Oops, sorry. D. Yeah, that's correct. So this is the d, and of course, that's exactly what you mentioned here, right?
So we can do it at first in our way to verify it.
Okay. Now do it on SO3. What is your way on SO3? It doesn't work. Okay. So does that make sense? Okay. You have to stop here. Okay. And next time, inshallah, we're going to be continuing. Okay. So far, okay. Let's see what we did. Let's just recap. We only introduced the differential of a function psi on a vector space W. Okay. Let me, in 1 minute, without explaining it, I'll show you how it looks like on a general manifold. Okay. And then we're going to be applying it next time on the SO3. Okay. But let's just use this couple of minutes. Okay. And also in case you want to stare at it at home. Okay. It will not make sense, but at least maybe you look at it before you sleep or something. Okay. So what is the differential? So part C, what is the differential of a function on a manifold M? So let a psi be a function that eats a point on the manifold and give you a scalar number. So it will eat an x in M and will give you a scalar number psi of x. The differential of psi is the unique covector d psi of x. Where does it live? Where do you think it will live? In the cotangent space to M at the point x. Okay. That satisfies for all, okay, or for any arbitrary delta x. Where would the delta x live? In the tangent space at the manifold at the point x. It will satisfy what? This expression. This is a covector. You pair it with a vector using the pairing definition of the tangent space at the manifold. So that's the new thing now. So in the previous definition, we used the pairing on the vector space, but here we use the pairing on the tangent space. And the tangent space, if you remember, it is actually a vector space. Okay. And this is equal to d by d epsilon. How should we proceed? psi of
Is
Psi
it,
of x plus epsilon
x plus epsilon
delta x.
x. Is that correct?
In the manifold, you cannot.
Can we say something like this?
For the manifold, no.
Why?
Because we do not have addition of
We don't have a plus.
Yes.
There's no such thing as a plus or minus on a manifold. So we have to generalize it. So we're going to be generalizing it by saying this is, we're going to be calling this term, let's put it in green, x epsilon. What is this x epsilon? Where x epsilon is a curve on the manifold defined such that if I evaluate x of epsilon at 0, I get x. So it's a curve that starts from the point x I'm talking about. And when I take the tangent vector to that curve, also at 0, I get the delta x, which lives in this manifold. Done. Definition is done. Okay? Okay? Of course, this is just an abstract definition. It does not have any meaning unless you tell me what manifold you're talking about. And after that, you tell me what is the pairing on that manifold. And then we can follow the same procedure. We just evaluate this term. We do the differentiation with respect to epsilon. We just simplify a little bit and look at the left-hand side and the right-hand side. We compare both. And whatever is remaining here, okay, that multiplied by or paired with the delta x, this arbitrary delta x, we're going to be calling it the d psi. Next time we do it on SO3, inshallah. Any questions? Okay. جزاك الله خير.